Hi everyone, this is Javier Juviere. I'm collaborating with Beth and Justin on today's webinar, where we are going to talk about setting up and interpreting DOE results in Moldflow Insight. So, yeah, as usual, your microphones will be mute. If you have any question on the way, you could just type it in this small area. We will get that, we will try to answer, but nevertheless, we have at the end of the webinar questions and answers slides, so we will try to answer all your questions. If anything is left, you could also do it on our forum. Okay, so as in other webinars, just a brief overview from what we have been done and what is coming. So if you have been attending the last webinars, you know that we were doing a webinar mixing Helios and Moldflow, and another one talking about the boundary conditions in Moldflow Insight. If you did not attend it to this webinar and you want to take a look, these webinars are posted in our channel in YouTube. For the next webinars we are preparing, so one of them is tips and tricks in Moldflow Advisor and exporting Moldflow results to a structural analysis package. As I said, all our webinars are placed in our YouTube channel under Autodesk Sim 360. So if you are seeing or watching this webinar already on YouTube and you want to join us live, you could go to our Autodesk simulation forums through our autodesk.com help webinars, through our Sim Hub events, or just writing us a direct email, just that we know about you, that we join in the list, and you will get periodically emails talking about the new webinars that we are going to host. Okay, so as you know, we are constantly publishing articles with the issues that you have running Moldflow. We are capturing this information and we are publishing in our Autodesk knowledge. And if here a short description of the last issues that we noticed is like a trend. So if you have something similar, you could read the articles. Nevertheless, you could also go to our AKN and take a look on other articles that maybe could answer your issues. As you may know, we are not publishing service packs anymore. We are releasing quarterly versions. So our last release was on 14th of July, is the Moldflow 2018.1. It's already on the Autodesk account. So if you are on subscription, you could go there and download it. If you're still running the 2017 or 2017 R2, we developed a new simulation job manager that address some issues on the previous releases. This could be also downloaded separately and installed along with Moldflow 2017 and 17 R2. So today's agenda, we divided in 4 different points. The first one is an introduction to design of experiments. Second, design of experiments options. A demonstration, so based on a simulation done in Moldflow, and reviewing and interpreting the results. But before we start with the DOE, probably you know, and this is a capture of our license levels from our help online, that not all the license, all the levels in Moldflow Insight are able to run DOE experiments. So if you take a look at the bottom of this screenshot, you will see that only premium and ultimate licenses are allowed or entitled to do this kind of design of experiments. The main reason for that is here on the maximum simultaneous analysis. So you know that one standard license allows one parallel instance of calculation or simulation, while the Premium and Ultimate one license contains, so it enables you to run up to 3 parallel simulations. So, and this is very important from what we are going to see now. So if we could click, yeah. Yeah, so designs of experiments is a little bit special in that sense. So we will see now during the webinar that the design of experiments is combining several variables to create a bunch of what is called runs. At the end are just jobs. And during the simulation of these jobs is always running in parallel the DOE analysis. So therefore, it's at least necessary to have 2 free instances of calculation in order to be able to run a DOE. The more licenses we have, the faster will be the DOE, because this bunch of runs, which could be easily goes up to 20 or 30 runs, will be simulated in the remaining instances that we have in our licensing. This makes also that the DOE could be a quite low analysis, because if we have, let's have a guess, 20 runs to run in a DOE, and we have 1 license, 1 premium or 1 ultimate licenses, that means that we are only able to run 2 runs or 2 jobs at a time in parallel with the DOE. And this will be sequentially until the 20 runs will be finished. Therefore, when we are setting up DOE analysis, it's very interesting to run it on the cloud. So in the cloud, we don't have this limitation of number of instances. And if we have quite big DOE analysis, that will speed up a lot the simulation of our analysis. So just a heads up. So for DOE analysis, we need at least 2 instances. And that's the reason why we need at least a premium and an ultimate license to be able to run a DOE.
Great. Thanks so much, yes, Javier, for discussing that information on the licensing. Now we're going to kind of get into the bulk of today's conversation. So starting with an introduction to design of experiments. So in Autodesk Moldflow Insight, design of experiments, or a DOE as we'll refer to it, is considered a type of optimization analysis. Optimization analyses are those that are designed to assist the user in producing the best possible part. Optimization analyses enable the user to change parameters in a virtual environment and see the effect on the quality of the part before any money is spent on production. Every analysis sequence in Moldflow has the option to run an optimization analysis. By default, as you can see here, the optimization method is always set to none. Here is where you can see that you have the option to change this to either a parametric study or a design of experiments. Today, we will be focusing mainly on design of experiments in Moldflow Insight, but I wanted to briefly touch on the parametric studies for you in the following slide. So, as mentioned, one of your optimization analysis options is to perform a parametric study. In a parametric study, specific values for the variables to be investigated are selected. Each combination of variable setting is run as a separate job. So this can result in a large number of analyses and potentially take quite a long time to complete. So for example, combining 3 values of mold temperature with 5 values of melt temperature will result in 15 different individual analyses. The results of a parametric study are presented in a table that can be filtered and sorted as required, and then individual studies can be opened and investigated further. So now what exactly is a design of experiments? So a DOE is a systematic approach for evaluating relationships between input factors and part quality criteria. It's essentially an engineering method that determines which variables in your design have the most and least effect on the quality of the final part. A DOE analyzes how the quality of a part changes as input variables change. DOE should be used early in the design stage to improve your designs. And the benefits to using DOEs is that you can obtain more and higher quality data about a problem. Again, a DOE is a structured, organized statistical method for determining the relationship between factors affecting a process and the output of that process. In this scenario, factors are inputs to the process. Factors can be classified as either controllable or uncontrollable variables. Examples for molding factors include temperature, pressures, and fill time. In an Autodesk Moldflow DOE, we will call these variables. Levels are settings of each factor or variable, such as the actual temperature values, the pressure values, or the actual fill times. Output is what you get from the experiment. In an Autodesk Moldflow Insight DOE, we will call the output results. And then lastly, noise factors are uncontrollable factors that induce variation under normal operating conditions. So examples would include multiple presses, work shifts, raw materials, or humidity. In an Autodesk Moldflow Insight DOE, we will not be dealing with noise. Design of experiments can be used to understand things such as the sensitivity of results to variables such as processing parameters, the interaction between variables, and the influence of a variable on a desired result. Performing a design of experiments versus at the press molding trials. So performing a DOE in Moldflow helps you establish process capability early in the product cycle. The DOE simulation identifies variables with significant effects on the part and assists in searching for the optimum part design in molding conditions. When comparing at the press molding trials to a DOE simulation in Moldflow Insight, they're costly and can cause material waste and excess machine time usage. They can also be time consuming as temperature stabilization periods are required when changing your temperatures. Today, there's extensive versatility when performing a DOE in Moldflow Insight. A DOE can be used with all available analysis sequences. So, for example, with cool, flow, overmolding, and MuCell. A DOE can also be performed with all model types. So that would be with your midplane, your dual domain, and your 3D meshes. DOEs can be used with common input variables, both single values and profiles. The quality criteria for a DOE includes all relevant results to the analysis being run and the ability to define critical dimensions and areas of the part for investigation. DOE results include variable influence rankings and 2D and 3D quality response surface contour plots. A design of experiments can be used in a number of situations. So, for example, a DOE can be performed to compare alternatives, such as determining which pack time is better for your part's warp. They can be performed to identify significant variables. So, for example, if your tool is pressure limited, which variables affect the pressure to fill the most? DOE can be run to target a specific output. For example, can I achieve a uniform packing within the available clamp force? Additionally, you can use a DOE to identify the optimal process, meaning what are the significant variables and what are the levels to achieve the best quality. So why use a design of experiments? DOEs produce orders of magnitude more information than a one factor at a time test at the same or lower cost. For example, if I have an experiment with 7 variables at 2 levels, a one factor at a time analysis of all combinations will require 128 runs. A DOE analysis can be done in 32 analysis runs. It is important to note here that performing a DOE reduces the amount of jobs that you need to run to get the same amount of information, and it obtains this information in a smarter, more optimized way. A DOE is like doing parallel processing versus serial. Additional advantages to performing DOEs include that the DOE estimates of the effect of each variable on results are higher in precision with less variability. The interactions between variables can be estimated systematically, and DOEs allow us to predict the behavior within the design space and allow limited extrapolation behavior outside that design space. Again, with a DOE, variables are selected and a range of values are specified for that parameter. The value you define in the process settings is the midpoint of that range. The DOE analysis determines the relative impact of those variables and recommends the optimum processing conditions based on the analysis criteria. Any numerical input for the analysis can be used as a DOE input. So some examples are shown here. Processing parameters such as pack time, mold temperature or melt temperature, and boundary conditions such as coolant inlet properties. So next, I'm just going to talk a little bit about your DOE experiment options before we get into some demonstrations in the software. So here you'll see that when you select a design of experiments, the DOE builder will appear for you. And under the first tab, which is your experiment tab, you have the option to pick between 4 different DOE experiments. The first one here is known as one variable. One variable calculates the effect of a single variable of your choosing on part quality criteria that you select. This is the fastest of the DOE experiments and is a good option if you're interested in the effect of only one variable. The results of this experiment are written in the analysis log. XY plots of the data can be accessed in the results section of the study task pane also. The second option here is the variable influences or the Taguchi. Variable influences DOE calculates the relative influence of each of the variables that you're interested in on the part quality criteria that you select. The variables are ranked according to their relative impact, with those variables having the most significance given a higher percentage than those that have less. Since these results are strictly percent rankings, they're written to the analysis log and no plots are generated. Variable influences is the recommended experiment if you are unsure of which variables to monitor. The DOE solver launches an optimized set of analyses to determine this ranking, and from the results, you can decide if you need to monitor all of your selected variables or just a subset of them. You're able to select as many variables as you'd like with this experiment type. The third DOE experiment option is the variable responses or face-centered cubic. If you know which variables to monitor, select the variable responses DOE to determine their effect on the quality criteria that you're interested in. In this experiment, a larger set of experiments is run than for the variable influences to extensively test the various combinations of your input variables. As a result, this experiment takes more time than the 2 previous options. The results for this experiment are written in the analysis log, as well as 2D and 3D response surface plots of the data are generated. The results can be examined graphically to determine the optimum conditions. And lastly here, we have the fourth option, which is the variable influences, then responses. Variable influences, then responses uses the Taguchi method to determine which variables have the most influence on specific quality criteria, and then runs extensive factorial experiments on the most significant input variables to determine how they impact part quality. This option should be selected if you're interested in the effect of the part quality on various input variables, but are unsure which input variables have the most significant effect. The minimum number of input variables for this experiment is 3. If you leave the default as 3, but select more than 3, all the selected variables will be ranked using the Taguchi method, and then the 3 variables with the greatest influence will be used for the responses experiment. Next, Justin's actually going to be demonstrating variable influences, then responses DOE for you here today. Just give me one moment and I'm going to send the screen over to him.
Thanks, Beth. So today I'll be going through a quick demo on how to set up a basic DOE and also how to interpret some of the results that you get from a DOE. To start, the first thing we'll want to do is pretty much determine why we want to run a DOE. So we want to determine our objective. For this demo and this part, our objective will be to find the variables that create a part with the lowest sink mark depth, a parting line flatness within tolerance, and ensure certain critical dimensions are within a specific tolerance. Good idea to begin would be to run an analysis without the DOE just to get some baseline results to make sure your process is within reason. Also, if a certain result is unacceptable, we can include that in our criteria to see how certain variables will change that result. In this demo, our baseline analysis will also allow us to set up anchor planes to measure our flatness in the DOE. So since I want to check for flatness and critical dimensions, I'll have to set up some boundary conditions first. So for critical dimensions, I already have some nodes labeled. So I'll turn off some of these other layers just so I can see them easier. And I'll just go up to boundary conditions and then critical dimensions and optimization. And then I just want to select this one and this one. And that'll be our width at gate. Apply. And then this one here would just be our length. And we can select any nodes. I just had these labeled just for time's sake. And then this last one would be our width at end of fill. And you can see a new layer is created down here with our constraints that we can turn on and off. So we can just turn everything back on. And then now we want to set up our nodes for flatness. So I can zoom in here. And it's the flatness of parting line we want to analyze. So I'll just click one of these dots, go up into mesh, and then we want to select nodes on same surface. So we can see that all the nodes are selected on that top surface. And then we can just save that as edge nodes. Hit OK. And then that'll be labeled up here as edge nodes. We've actually had a webinar in the past utilizing boundary conditions you can find on our Autodesk Simulation YouTube page if anyone's interested in that. So now I can pretty much run the analysis just to get my baseline results. So I'll open this. This is already completed. So now that I have my results, I can actually set up my anchor planes. So I can go down into my deflection Z component. And I've already set it up. So I just wanted to put my anchor planes to make my parting line surface flat. So to set up a DOE, as Beth mentioned, the DOE options is under optimization. So we can just double click on that, go into design of experiments. You can see whenever I clicked on that it didn't delete my results, because the results that we put in the process settings would be our middle values for our variables. As Beth mentioned earlier, a variable influences, or Taguchi analysis will give us the variables that most affect the quality criteria that we have defined. A face-center cubic, or variable responses, will show us the interaction between variables in a nonlinear way. And what we'll be running today is the variable influences and responses, which will run a Taguchi analysis, and that'll determine our top 3 influences on our set criteria. And then we'll run a variable response study using those 3 influences. And you can set how many variables down here that you want to transition from the Taguchi to the variable responses, but 3 to 5 is typical, so we'll just leave it at 3. This is where we can select our variables. We'll select a couple here, and we can set the min and max values for each. So I'll just leave them at default, but our middle value, as I've said, is in the process settings that we've set originally. So we just select some of these, pack duration, pack pressure. And then down here, there's geometry information. And since we've actually put our ribs on a separate layer, we can select that, and we can select our ribs. And we can actually alter the dimension scale by 25%. So that'll see how varying the ribs by plus 25 and minus 25% will affect our part. Something else interesting that we might be able to do is, if we had our gate beam elements on a separate layer, we could actually add that as well and see what would happen if we would change the gate size. Next tab is where we'll set our quality criteria, so what we're actually looking for. We can turn everything off here. The main thing we want to look for is sink mark depth. So if I select that, each quality criteria will need to set the weight, and this refers to the importance we placed on the specific quality criterion. A higher number will mean that it is more important for part quality than other criteria. So for sink marks, we want to set it to 10, since that is important to quality, and a lower value will indicate a better part. Something to keep in mind is that we'll be calculating for maximum sink, and our goal is to minimize it across the part. And something else to keep in mind is that the value for some results isn't always an exact number like sink mark value would be. It could be a standard deviation or a variation from the average. If we look at the temperature at flow front, we can see that it's calculating standard deviation. And that's because the goal would be to minimize the variation in the temperature across the part. We also want to check our critical dimensions we had set up and our flatness. So down here under warp, we can go to new warp criterion and select the critical dimension. So this is where we can select our length, end of fill width, and end of fill or width at gate. So we just select that and hit OK. And we'll just leave these values at 1, since a specific low or high dimension doesn't really mean we have a quality part. We just want to see how those variables influence the dimensions. So we can add this one and add the last one. And then to add our flatness, we can select here and select a node list, and this is where we selected all those nodes on the top surface. We can hit OK, and the result is deflection all effects. Our component is just going to be in the Z direction, since that's the parting line. And this is the anchor plane we had set up here. And for this one, we'll actually set our weight to 10. Since the value calculated will be a standard deviation, we're not really looking for a minimum or maximum number, because the flatness can warp in either direction of the parting line, but we do want to minimize that variation between the minimum and maximum. And then the very last tab is the options, and this is where we can decide if we want to keep the results for all the analyses that are run, so we can go back and look at each analysis as a separate study. Keeping this checked can take up a good bit of space, since we're basically saving, which would amount to 23 analyses. Then we can finish, and we're good to run the DOE. So I've already ran it, so we'll just open that up. One of the first things we can check is we can go into the log file just to see some information. We can pull up the DOE log at this last tab, scroll up to the top, and we can see which type of analysis was ran, which was the double analysis. The first analysis was the influence, or Taguchi. We can see the number of variables that we had set, the number of quality criteria we have set, and then we can see the variable information that we set. So the dimension scale factor, so the ribs was -25 and +25%, and all of the other information. We can see the quality information and the weight we gave each quality, and then the Taguchi analysis will run. And down here, the results we get are the variable influences on each quality setting. So we can go in and see that the variables we have set, how much of an influence they had on each specific quality. So we can see at sink mark depth here that pack duration had the biggest influence, while melt temperature and packing pressure had the second and third. For flatness, again, pack duration had the biggest influence, and second was the rib width, and third was mold surface temperature. If we scroll down a little further, we can see the influence on global weighted quality. So this is taking everything together, taking into account the weight that we set on each quality criteria, and the top 3 influences are used in the next step of the analysis, which is the variable response. So we can see here that our top 3 that it's going to take into that next analysis is pack duration, packing pressure, and melt temperature. So second analysis started, its responses. It's taking 3 variables, 5 quality criteria, and it'll run the analysis. Then we can scroll down and we can see that it's going to give us the optimum variables for each specific quality criteria. So for sink mark depth, we want the minimum value, and that's going to be at the higher pack pressure, the higher pack duration, and at 356 Fahrenheit temperature. We can see on flatness that the minimum standard deviation that we want is going to be a high pack duration, high pack pressure, and a little bit more of a melt temperature than the medium value that we initially put in. So now once we go through this, we can actually go out and look at some of the actual result plots. So we can turn that off. And we'll go down to the bottom here. We can see that a bunch of result plots are generated. And the first thing we can look at is the Results Comparison Explorer. And this will bring up all of the analyses that we ran, all of the settings that were used, and some of the results that we have set for the quality criterion. By clicking on the checkboxes over here, we can actually choose each specific analyses and add those to the study, to the projects we can look at as separate studies. If we wanted to see the specific studies that had the lowest and highest standard deviation value for flatness, we can, it says edge nodes here, so we can just sort it, and we can select 2 since it has the lowest, and 7 which has the highest. And then we can just hit add selected studies to project. Once we do that, we can see that it made a new folder over here that has each of the studies we can open up and view all the results separately. Next are the DOE specific plot results, and the resultant plots that show up down here are dependent on the DOE experiment type and also the type of mesh that was selected. So opening one of the results down here, like we'll open up volumetric shrinkage. We get a control panel over here that has the top 3 influences, which was pack duration, pack pressure, and melt temperature. I don't know why I can't drag that. Okay, so that should be good enough. You can see if we alter these values that we'll actually get an update in real time of how these changes affect our volumetric shrinkage. So if we turn the pack duration to the higher value, the pack pressure to the higher value, and the melt temperature to the lower value, we'll see that we get a low volumetric shrinkage, while if we just alter some of this stuff, we'll see that it goes higher. So there's also response surface plots that are added as well, and these are for the specific quality criterion we have set. And these plots will show the top 3 influences, and it'll show the effect that 2 variables have while keeping all of the other variables constant. And a good way to set this up to look at it is to orient your z-axis, which is the quality criterion that you're investigating, to be vertical, and from low to high. And then we can alter stuff down here, like melt temperature. We can just see how it's affecting. And essentially, by looking at the slope of the x and y curves, x is pack duration and y is pack pressure, we can determine how much of an influence those variables have on this result. So the more parallel the slope is to the x and y plane, the less of an influence that variable will have on flatness. So looking at this result, the packing pressure, which is the y, is kind of parallel to the x and y plane, so we can determine that this doesn't have much of an influence on flatness. But if we look at the x slope, it has a huge variation, so packing pressure does have a large influence. So that's pretty much a basic DOE. We can look at some of the other results, but I kind of wanted to touch on a basic parametric study real quick. The parametric is in the same location, the optimization settings. So we can go in there. And if we select parametric study, it looks pretty similar to the DOE builder. And when we click on a variable, we don't have a middle value. We just have multiple values that we want to investigate. So if we just want to check the mold surface temperature, and we want to go 104, and we want to check 120, and maybe 140. You can see the number of analyses down here updates. If we click on something else, 1.5, if we want to go 1 and 2, the number of analyses will update to 9. So that's going to figure out all the different combinations available. Another difference with the DOE is if we want to investigate multiple rib widths, we can actually put in specific values instead of just percent scaling. And we can do that by making CAD modifications in the CAD part. So we can turn off some of these other layers and make sure the CAD body is turned on. We can go up into geometry. In this modify CAD surfaces here, we can click on that and go normal. If we select normal, we can modify the size of the ribs, and if we select vector, we can actually move that entire feature. But if we select some of these rib faces, so select that one, that one. Button's not working. Okay, there we go. And then we'll select the other side as well. We'll just alter that by 20 thou. And then we can hit preview and we can see how those rib widths are updated. Now if we hit apply or just hit enter, it'll update our CAD geometry permanently. But if we just want to try out some different rib widths in the parametric, we can save it as a CAD modification, and then we can just name it rib width. Just hit OK, and then if we close out, we'll see that it goes back to the normal value, and our CAD modification will be saved up here. So then we can go into optimization, parametric study, and you can see that the CAD modifications list, we have rib width available. So we can click on that, and we can actually put in some extra values to test out what would happen if we would alter that rib width. So after the study is completed, we can open up some of the results. And you don't get as many results as a DOE, but we do get a results comparison explorer like a DOE, where we can look at all the analyses that were ran, so 6 analyses, and there was modifications for the CAD, so the rib width, so 20 thou and 40 thou. And also we alter the melt temperature. And like I said here, if we're looking at sink mark depths, we can sort by that. And then 3 has the lowest and 5 has the highest. We'd be able to add those to the project. We can go over here and see that those are added to the project, and then we can open those up individually and look at the results. So that's all for the demo today. So I'll hand it back over to Beth for a closing summary and a short Q&A session.
Great, thanks so much, Justin. So a summary for today. In order to perform a design of experiments, as Javier had touched on, you need at least the premium or ultimate license. You cannot perform a DOE with a standard license. That also makes me want to touch base on, I did see a question about how long or what system was used to perform the DOE that Justin demonstrated today. I do know he ran that in the cloud. He may be able to chime in here in a minute on how long that analysis took to run, but we are going to zip up the study file along with results and place that into our Autodesk box folder that we'll be sending out here today after the demonstration. I'm sorry, after the webinar. Basically, so a DOE is a systematic approach for evaluating the relationships between the input factors in your part quality criteria. And a DOE analyzes how the quality of a part changes as input variables change. DOE can be used to understand the sensitivity of results to variables, the interactions between variables, and the influence of a variable on a desired result. There's extensive versatility when performing the DOE in Moldflow Insight. They can be performed with all available analysis sequences and all mesh types. DOEs produce orders of magnitude more information than a 1 factor at a time test at the same or lower cost. And again, these are the 4 types of DOE experiments that you can run in Moldflow Insight. They are the 1 variable, the variable influences, variable responses, or the face-centered cubic, and then lastly, the variable influences, then responses, which is what Justin demonstrated for us today. All right, and with that, we can see if there are any more questions in here. I know we've been trying to keep up with answering them along the way.
Beth,
yes.
I can comment a little bit more on the time to run.
Yep, absolutely.
Yeah, for the example done, remember we did a Taguchi and then the face-centered cubic, and so effectively there's 2 sets of analyses run, and so the Taguchi required 8 analysis runs, and then the face-centered cubic required another 15, I believe. And so then it boils down to, as Javier was talking about, how many licenses you have available. So if you're running on the cloud, for instance, you can run all 8 in that first group and all 15 in that second group, essentially in parallel, so it becomes very fast. But then if you only have a single, say, ultimate license, you can only run effectively 2 analyses at a time, then that DOE is going to take a little bit longer. Obviously your system configuration has a lot to do with that.
Yep.
And so it really depends on, how long it takes to run the analysis just on a single normal, say, fill pack warp, and then your license is available and the DOE that you set up.
Yep, perfect. Thank you, Jay, for adding that. Are there any other questions you see here, Jay, that might be good to touch on? I'm just taking a quick look now.
Beth,
Yes.
I could see one question. Can parametric studies and DOEs run on a Linux server yet? So I will say yes. So one of the limitations that we have before in Linux was that we were not able to run meshing. But since I could not remember which release in 2017, we are now able. And I will say yes, should be possible. But yeah, we could check that, and if it's not, we could just post it in our forum.
Okay, great. See, so there's a question here. What are typical roadblocks to getting this to work on real parts when you want to adjust geometry parameters? How clean does the CAD need to be? Let's see. Jay, do you have any ideas on that one?
Pick on me. Thanks, Tim. Anyway, I honestly don't know. I've played around a bit with the geometry parameters and what you can move. If the CAD is not watertight, right, it's going to be a problem to mesh. And doing the moving of the geometry may be a problem. So I think that it's an all depends case. I think what it boils down to, I was in fact playing with a part just the other day, and depending on how I picked the CAD faces to move, it didn't like it, and it created some strange things, and I changed the options in the moving, and it worked fine. So there's some of that goes on too. I wish I could be a bit more specific with that, but that's what I know.
Sure, thank you. Question here: Can is a DOE available for all molding processes? Yes, for that. So it is supported. I'd say with all of your molding processes, you would just need to turn the optimization option from none to either parametric or DOE from your molding. Well, go ahead, Jay. Do you have something to add?
Yeah, that's absolutely right, with a couple caveats.
Sure.
Things that are already quote-unquote optimization, like molding window, runner balance, it isn't supported. But the types of processes that was listed there, gas injection, U-cell, all that absolutely is supported.
All right. Great. Let's see what else is here.
So Beth?
Yes.
I see here one question. Is DOE can be done for different part thickness and also for some local area? Well, actually, for different thickness it could be done. So it's the same example that Justin made for the rib could be made for the complete geometry, or for some, well, the geometry should be able to be recognized by a surface, and then applying this vector or shift of the face could be done with different thickness. So actually, the answer will be yes, it could be done.
There's another way as well for mid-plane and dual domain, because for both of these mesh types, there is a parameter of thickness that we can define. We can define the thickness directly to the elements. Of course, this is how we directly define mid-plane elements, so it's no issue there. And as all of you, I'm sure, are aware, if you modified the thickness property of a dual domain mesh, it's very valid for flow, but not so for cooling and warp. So there's a little roadblock there, a little limitation, but you absolutely can change the property of the elements, and essentially you do that by layers. So the elements that you want to change, you put on a separate layer, you specify that layer, and then in the DOE parameters you can say the percentage change of that layer. So it works a little bit different than what Javier was talking about with the geometry.
Yes, and with the 3D mesh.
Yeah, right. And with the 3D meshing and dual domain, you can use that geometry modification, which is a little bit stronger in some ways. But you've got a couple of ways to do it.
So I see a question here. Does using the CAD modifications retain the node numbers when that is run, primarily if node lists are used? So I'm going to show my screen and just show you when I ran that parametric and I altered that rib width from, increased it by 20 thou and 40 thou. Over here, this red one is the original, and then this one's the 20 thou, and then this one's the 40 thou. You can see if you zoom up on that edge that the original had an extra node here, so it remeshes, and it doesn't always mesh in the exact way, so it probably is not going to have the exact same node. So I don't think you can use node lists because it remeshes when you make those modifications.
Great, thanks, Justin. And then let's see here. All right, and it looks like we have one more question here. Can warp shape results be exported when CAD modifications is used? Is this functionality available in both dual domain and 3D meshes?
So since I just showed you, it does remesh when you make those CAD modifications. So you would be able to export that warp shape.
Great, thanks, Justin. I think that's everything in the questions there. And again, if you do think of anything after the webinar, or if you rewatch the webinar later and it prompts any more questions, please feel free to post to our forums there, and we can take a look for those questions in there. And with that, we just wanted to thank everybody for attending. Again, the slide deck as well as any sample models used in today's webinar will be uploaded to an Autodesk box folder, and an email will go out later today with a direct link to a YouTube video recording as well as to the Autodesk box folder there. All right. Thanks, everybody, and have a great rest of your day.